In this video, we are going to solve the Fall 2018 Test 3 Roadmap. I created this roadmap from my imagination, so I hope that you feel ready to think about it. Where do we even start on this roadmap? Looking around. There we are. Start here. We have to start with benzene. A large part of this test is putting groups on benzene. First reaction, start with a zinger. This one's not even in the book. We're supposed to look ahead a little bit for clues here. We're going to create something here, obviously some kind of reduction under severe conditions, 500 atmospheres. And something like cyclohexane looming in our future, because that's actually a box there, which means it's produced by this reaction. I'm actually thinking cyclohexane myself. Yep, here's cyclohexane, chair form not necessary. You could draw a hexagon if you want. Next job is to take cyclohexane and convert it to bromocyclohexane. That is found in section 8.2, which is radical halogenation of alkanes, and it's accomplished with a halogen and heat. In this case, bromine being the required halogen and heat. There's a mechanism that has an initiation and 2 propagation steps if you want to look back at it. Moving forward, we've made our bromocyclohexane. It's going to react with this major product down here. With aluminum chloride present, I'm thinking that major product has a benzene in it. That's a catalyst we use to put groups on benzene. Why don't we tackle that next? Oh, by the way, this section number here, we didn't know because it wasn't in the book. This one, we're putting a bromine on benzene first, using bromine and a catalyst generated when bromine reacts with iron. That's iron 3 bromide. And then nitration. So it's important to note that bromine, once it's on benzene, is an ortho-para director, with para being major and ortho being minor. There's our 2 products. Bromine on the benzene in step 1 and a nitro group from nitration in step 2. So we have para-nitro-bromo-benzene, para-bromo-nitro-benzene, and ortho-bromo-nitro-benzene as our 2 products. Bromination is found in section 22.2a. And 22.2f reminds us where the next group goes. It's called directing effects. And 22.2b tells us how to put a nitro group on benzene. Moving forth from our major product right here, we are doing a Friedel-Crafts Alkylation using our bromocyclohexane and aluminum chloride catalyst. Friedel-Crafts Alkylations found in 22.2d. We're going to put a cyclohexyl group on the position indicated by bromine being a more powerful director than nitro. Bromine being an ortho-para director will direct the next group to the ortho position because para is already taken. And the molecule is going to look like this. We have bromocyclohexyl nitrobenzene. Potassium dichromate sulfuric acid in water with heat. We'll do an benzylic oxidation on this position right here. And that will be a carboxylic acid, and these carbons will fall off as side product. That is found in section 20. Oop, I think I erased something I didn't want to. 21.5. And the result is here. And rotating it so we can see things a little better. In fact, looking ahead, if I rotate the bromine to here, that's really going to help when I'm kind of looking over here. Maybe a little more. CO2H straight up. Got it. Now the question is, how can I make an ester? That's a classic Fischer esterification. And the chemicals are ethanol and sulfuric acid and heat. Nitro group has to become fluoro. We'll talk about that in a second. A reminder, Fischer esterification and all other condensation reactions are assisted using a Dean-Stark trap. Not mandatory, but helpful. We now also have to convert a nitro into a fluoro. We do not know how to do that. We do know how to take this diazonium ion and make it into a fluoro. So our job first is to make a diazonium. Our only way to put fluorine on benzene is from a diazonium benzene. Nitro groups cannot directly be made into diazoniums either. Only anilines can. So job 1 is to reduce NO2 to an NH2, an aniline. And then job 2 is to make a diazonium species. And then our last job is to convert the diazonium to a fluorine. All of the information you need for these transformations can be found here. Fischer esterification in 17.3c and 22.3 for the protocol you're about to see right here. H2 and nickel reduction of the nitro to NH2, diazotization using sodium nitrite HCl and keeping it cool at 0 degrees. We'll get to your diazonium ion here, and the final step is to treat it with fluoroboric acid and room temperature. Sorry, it didn't quite fit in the box. And that gives us this result here. We'll look carefully at it. It does appear to be a dead end, so we don't have to go further from there. But we're also taking this same molecule here and converting it to this. What transformations are we seeing here? I'm just going to rotate this around here. And the bromine set up on top. Now it looks like the CO2H needs to become a CH2O. That is just a good old reduction of a carboxylic acid to an alcohol using lithium aluminum hydride followed by HCl. You can find that in section 17.3e. And 22.3 talks about converting a nitro to an amino in a reduction reaction accomplished using lithium aluminum hydride and HCl. That's going to accomplish two things if I use excess. Let's write that down. By using an excess lithium aluminum hydride and HCl, we converted CO2H into CH2OH, which we can make into an ether shortly. We also, by using excess, converted a nitro to an aniline. And that is done down here. Now time to make an ether. We learned how to take H's off alcohols, so we're going to take the H off this alcohol we just made. And then an SN2 reaction using benzyl bromide. That will be our reagents. Realizing that's a two-step process here, I adjusted my green numbering. And we've arrived at this molecule, which is also a dead end. Moving on. Back. Alright, we didn't make this yet. What has happened here is a whole bunch of things. Oh, we made that. Sorry. Not so many things. I gotta read my arrows more carefully. This arrow zigzags through the box and ends up down here at phenylethanone. Phenylethanone looks like this. Here's phenylethanone. It looks like the new group is in black. And that would be accomplished by using acetyl chloride. This is an acetyl group in black. I'm going to put a ketone on there. We'll learn how to do that. Friedel-Crafts Alkylation in 22.2e. And here are the chemicals. Acetyl chloride and aluminum chloride. Now, how do we make this ethylbenzene, which is just this portion of the molecule, from the ketone? Well, that's reduction of a ketone all the way down to a CH2. You can accomplish that with a Wolff-Kishner reduction or a Clemmensen reduction found in 16.3M. The chemicals here for the Clemmensen: zinc amalgam and hydrochloric acid will give ethylbenzene. And that is another dead end. Moving back, we have benzene becoming para-toluene sulfonic acid. That looks like this. So 22.2D tells us how to put a methyl on. Now the question is, why do I have to put the methyl on first? Well, methyl is an ortho-para director, and my sulfonic acid has to be para. If I chose to put the sulfonic acid on first, the next group goes meta, and that's not where the methyl is. That would be a bad choice. So first, put the methyl on. Next, put the sulfonic acid on. Here are the chemicals: methyl chloride with aluminum chloride, and then sulfuric acid and heat, also known as fuming sulfuric acid. Taking para-toluene sulfonic acid and nitrating it, and if you study directing effects, once again found in section 22.2F, you'll see that of these two, the methyl is by far the most important. It's an ortho-para director. It activates the ring towards reaction, whereas sulfonic acid deactivates it. So methyl wants to put the first group para. Can't do that here. Para is already taken. Nitration, which is what's happening here, will happen on the ortho position, giving this result here. Here's our resultant molecule. And if you want to look at it and then look at this molecule, maybe, perhaps, if you rotate it, first I'm going to flip it, just for your visual pleasure here, so that you can see things a little better. And there you go. Sulfonic acid here, nitro, possibly converting to cyano, most definitely now, and the methyl staying methyl. Looks like we have to get the nitro to be something we can convert to something else. That sounds very familiar. Nitro eventually becomes diazonium, and diazonium becomes fluorine. Same protocol to make the nitro into the diazonium. Everything is locked up in section 22.3. So I'm going to steal this part of this answer, renumber it, and come back to you. So the question is now that I have a diazonium here, you will not have that. You will have this diazonium. That's step 2. And then the chemicals that will convert diazonium to a cyano are KCN, potassium cyanide, and copper +1 cyanide, copper 1 cyanide. And there you go, you have a cyano compound, which is far from a dead end, isn't it? It's going everywhere. Looking, sometimes these things get rotated just to fit them in these areas here. So you want to think about this one. Whoa, grabbing stuff I don't want to grab. Just trying to rotate it so the sulfonic, there we go. They're the same except for cyano has to become carboxylic acid. That reminds me that cyano is a carboxylic acid derivative, and a carboxylic acid is right here. That is called hydrolysis, and it's found in section, I'm going to be erasing the section soon, 18.3a, and hydrolysis is with water and sulfuric acid. hydrolysis giving carboxylic acid. Now going up this direction, using this arrow, it looks like some weird stuff's going on. 2-methyl-aniline 5-sulfonic acid looks a lot like that. So let's just kind of sneak this over here, point an arrow to it. So thinking about this, we got the 5 for the sulfonic acid. I'm looking at this product I'm supposed to make here. I've got a methyl for 2, 3, 4, 5. And we need an aniline on 1. So the question is, how can I get an aniline here where I already have a carbon? I don't want that carbon. And I say, okay, I know if that was an amide, I could get rid of the carbonyl. This is bringing to mind the Hofmann rearrangement here. So I need to get an amide from an acid. Step 1 is to convert it to an acid halide. That's 17.3D. Thionyl chloride and pyridine. Step 2, acid halides can be converted to amides using ammonia in this case. I need NH2 attached to my carbonyl. And then the Hofmann elimination is found here, and the chemicals are here. Here are your chemicals. Ammonia creates the amide. Excess sodium hydroxide, aqueous, and bromine gives the Hofmann rearrangement. And you are now missing your carbonyl and keeping your amine. Giving this result here, I hope you can see the whole molecule. Okay, is that a dead end? Apparently not. We have to make this molecule here, which looks like this. What has happened is we've put bromines on this position here and this position down over here, which would be ortho to the NH2 and para to the NH2, and then the NH2 was made to disappear. Interesting. That's done using a diazonium procedure as well. First, we're going to take advantage of the fact that NH2 is a strongly activating ortho paradirector and brominate this molecule using excess bromine. Step 1 puts our 2 bromines on here and here. Step 2 makes our amino group into a diazonium, which we see up here. And the diazonium is converted to nothing. There's no such thing as nothing. There's a hydrogen here using hypophosphorus acid. I am sorry, that escaped me for a second. Hypophosphorus acid being right here. H3PO2 at room temperature will get rid of our diazonium and replace it with a hydrogen as required by the name given here. Moving right along. We were dead ending right there, so we didn't carry on in this loop down here. So that's where we're going now. We're going to take this molecule and convert it to this, which we already did. And then we're going to make the carboxylic acid into something that's reduced down to a CH2. I'm thinking CH2OH is easily converted to CH2Br. That is another lithium aluminum hydride reduction of a carboxylic acid. And we've done that already. Lithium aluminum hydride reduction to the alcohol, followed by PBr3 treatment to the alkyl bromide. And now we have to convert a carbon that has a bromine on it to a carbon that has a new carbon and a sorry, I almost gave away my thoughts. Here's the carbon off the benzene. There's a new carbon and an NH2. there's a beautiful nucleophile called cyanide that has the carbon and the N, which can be reduced to the NH2 with these sections in your textbook. 9.1 for an SN2 reaction and reduction to an amine in 18.3 E3. Chemicals listed here. Potassium cyanide in a polar aprotic solvent for an SN2. Lithium aluminum hydride reduction and HCl, giving your required product. Moving on, we never went down in this direction to a parent dead end as well. H2 and PT reduction of nitrile gives what we were just looking at. Gives us CH2NH2. So this resultant CH2NH2 from the reduction of the nitrile, and I think we've dealt with everything from up here to the right of the page. It's time to start a new thread going to the left. We learned that we can put a nitro group in section 22.2b, and it's a meta director, so my next group goes in the meta position. I'm looking for a meta bromonitrobenzene. So here's our meta bromonitrobenzene. We're supposed to react it with some reagents that convert it to 3-bromoparatoluidine. Interesting. We have to look up what toluidine is with information on question 17 in the multiple choice, where it says toluidine is methyl aniline. Here's the molecule. Paratoluidine is para-methyl aniline. And we already have the nitrogen. We need to reduce it to an NH2. The question is, do we do the methylation? We need a methyl group here. Do we do that before reducing the NO2 or after? If we try to methylate this with methyl chloride and aluminum chloride, the bromine takes over. It's an activator, and it wants to put the next group here, para position, or ortho here. Ortho being minor. But if this was an NH2, that's the most powerful ortho-para director we have, and it's going to make this reaction very easy after we put the NH2 there to put the new methyl group on the bottom. So that is our answer. 22.3, we're going to reduce the NO2 to an NH2, and also we're going to use directing effects and methylation. Hydrogen and nickel is another way to reduce the NO2 to an NH2, and then we'll take advantage of the NH2's para-directing abilities to put the methyl group on the para position. Now, we want to go to the left and make 5-bromo-metatoluidine. Metatoluidine would look like this molecule, but with let me just write metatoluidine here for a second. Right here is metatoluidine without the bromine on the 5 position. Toluidine is defined as methyl aniline. Aniline makes this carbon number 1 here, 1, and meta puts the methyl on 3, 4, 5 for the bromo group. So the product has the bromo group right down here, which, if you think about it, is the same as our molecule here. The bromine's where it needs to be, the nitrogen after we reduce it. But we need to get a group meta to the nitro. If I reduce the NO2 to an NH2 first, then we already saw your next group's going down here. Here I want to take advantage of the fact nitro strongly deactivating towards putting groups here, here, or here, but not as deactivating there. So we're going to methylate and then reduce. I think we just switched the sequence of these two up here. Methylate first, then reduce the nitro. Now we want to make this into this. This is the one where we have to go through a diazonium again, way over here on the right side of the page. I'm circling it. We have to make that first. These are the chemicals. Reduce, diazotize, and I'll renumber them and come back. All of this found in section 22.3. H2 nickel reduces to NH2, sodium nitrite, HCl aqueous in 0 degrees, converts to a diazonium ion up top, N2 with a plus, and then we react it with water in room temperature, and we get that red phenol up there. Next, we're setting up a Claisen by first doing an acid-base reaction, and then following it by an SN2 with an allylic ether. After the SN2 reaction, you have an aryl allyl ether, and that is a setup for a Claisen rearrangement. In section 21.4a, where 3 will end up bonded to the ortho position here. Now the question is it this ortho position, which is one away from the BR, or is it this ortho position that is para to the BR? It's going to get a bond to carbon. Sometimes we have to look ahead for clues. The major looks like it will be giving a result where there is a new carbon bond para. There's a new carbon bond para to the bromine. So it looks like less steric hindrance might be the reason for the group going there, and the minor would have to be just attaching this carbon to carbon 3. A lot of talk. Let me just show you the products. Maybe we'll talk through it. Major with the group away from the bromine, and minor with the group closer to the bromine. There were clues for the group itself in this next product up here, which, if you look backwards, is the same all the way back to our starting molecule. And what's going on? Going from here up to here is an oxidation to a quinone. We can find those section 21.4c, and this could be a record on a roadmap without seeing potassium dichromate, sulfuric acid, and water until now. Yes, oxidation of phenols to paraquinones is accomplished using chromic acid oxidation. This is one of the ways to make chromic acid. And then reduction of quinones to dihydroquinones is accomplished with our favorite reducing agent, lithium aluminum hydride, HCl. And I will copy that from here and edit that out. There's no cyanide. So there's our reduced quinone from our quinone. And we're getting there. Where did we leave off? We came down to these two and did not do anything with this one. This one's a little simpler than I first thought. It looks like this O ended up on this carbon, and if I could make that into a carbocation, that would do that. And it seems to me just protonate it with a strong acid, and that'll get us there. Oxidation from a phenol to a quinone is accomplished with chromic acid. Section 21.4c tells us how to do that. Reduction of quinones, this is a quinone here, to dihydroquinones is accomplished using lithium aluminum hydride, HCl, found in the same section. We left off our roadmap down here, needing to become this, and if you think about it carefully, one of these carbons just needs to become a cation. The O will just attack it, and sulfuric acid will make a cation on one of those positions, 50-50, and this would be the O attacking the cation. And what's going on from here to here is interesting. We have a new carbon-carbon bond to this group here, where the OH is one away from the thing that got attacked. If we can make this into an attacker like an organolithium, I'm thinking about attacking an epoxide right here. Got to see some work behind the scenes there. It's already an extremely long video. I've been at it for a while. So, there's my epoxide, HCl, generating this. We're almost there. I need to make an amino group where I used to have an alcohol. No good direct way to do that, but I do know if my alcohol is a ketone, which is oxidation, I can make an imine or an enamine. In this case, it would be an enamine, and then reduce it. And I don't think that's found in one section in the book, but one of the sections, the reductive amination, is found in 16.3L. We have to add PCC oxidation and then call it a day. PCC oxidation converts this OH to a ketone. HNET twice makes an enamine, where the nitrogen would be here and here, double bond. More major would be there, minor would be here, and then reduce that with H2PT. You don't have either one. You have your final product. And finally, I hope you found this video on the Fall 2018 Test 3 Roadmap to be useful. I look forward to our next video.